Through the diffraction, actually, we can look it up from the table, or actually we can calculate it by using the virtual work method, or the conjugate beam, or the double integration method. From the diffractions, actually, we can calculate the so-called support reaction. And after finding the support reaction, we can find the remaining support reaction using the equilibrium equations. And then from the support reaction, we can draw the shear force and then the bending moment diagram. Okay. And then tonight we will talk about another one, which is also our method to find for the support reactions. But instead of using the force as a consideration, right here we will use the so-called slope diffraction equations. But in this slope diffraction equation, actually it is an expression which relay the member end's moment to the diffractions, like the member end's rotation, the diffraction of the member, and then the forces within the member. This one actually is quite convenient. And then once you have the expressions, then you just write down the available diffractions. And then finally, by solving the diffractions, you can find the unknown support reactions. Okay. So for here, we will talk about the displacement method of analysis, some general procedures. And then we will mention about the slope diffraction equations. We'll use it for analysis of beams, and then use it for analysis of frames with no sideway, and then for the frames with sideway. Okay. So here I will just review the method for the force method quickly, and then we will go to the procedures for the displacement method. But here is just the revision for the force method. As I mentioned before, here actually we have indeterminate structures. For this member, actually we have 1 support reaction, 2 support reaction, 3, and then 4 support reactions. And then we just have 3 equilibrium equations, so we cannot solve all the support reactions. What we need to do is actually choose one of the support reaction as redundant, and then we will take it away. So for here, we choose the support reaction of B as the redundant support reactions. We take it away, and then subjected to the loading, you can see that the diffractions, delta B1 is equal to 5 FL cubed over 48 EI. And then, well, we will add it back at another support, another structures. You can see that for the one below here, actually we will add the support reaction back to the structures. And then you can see that the support reaction is equal to YBL cubed over 3EI. By considering the superposition, actually delta B1 and delta B2, when they are adding together, the diffraction should be equal to 0. Because actually the diffraction at the support right here is equal to 0. So you can see that delta B1 minus delta B2 should be equal to 0. Because at the support, the diffraction should be equal to 0. So you have 5FL cubed over 48 EI minus YBL cubed over 3 EI equal to 0. So from that, you can find that the support reaction YB is equal to 5 over 16F. So this one actually is quite straightforward, and then to find the redundant support reactions. And then for the redundant support reaction, it can be a force or it can be a moment. For here, you can see that we will choose the fixed end moment. Right here, we have a moment here. We have a support reaction here, and support reaction here. We have chosen the support reactions as the redundant. We take it away, And then you can see that because there's no fixed end moment, there will be a rotation here, which is called theta A1. And afterward, we will add back this redundant support reaction, which will cause a so-called rotation, theta A2. And then you can see that at the fixed end, actually the the rotation will be equal to 0, right? So theta A1 plus theta A2 should be equal to 0. And actually from the table, diffraction table, or from the method of calculation, like the conjugate beam or the virtual work method, then we can find that theta A1 is equal to FL squared over 16 EI, while theta A2 is equal to MAL over 3 EI. And then you use theta A1 minus theta A2 should be equal to 0. Then you can find that MA is equal to 3 over 16 FL. So just like what we have done in the last example, we can find the fixed end moment. And actually this method can also be applied to multiple, not just a single degree of indeterminacy. As you can see here for this example, we have 1, 2, 3, 4, 5, 6. We have 6. The degree of indeterminacy is equal to 6. It's equal to 3 should be, because you have 3 equilibrium equations, but you have 6 unknowns. So the degree of indeterminacy is equal to 3. So in this example, we need to remove 3 redundant reactions. We choose the support reaction at B, C, and D as the redundant support reactions. And then we take it away. And so you have the diffraction as B, as C, and then the D. We call it delta B1, delta C1, and then delta D1, okay? And then you add back the redundant support reaction. You add back RB, you add back RC, and you add back RD, okay? When you add back RB, you will have delta B2, delta C2, and delta D2. When you add back RC, you will have delta B3, delta C3, and delta D3, okay? When you add back RD, you will have delta B4, delta C4, and delta D4, right? Then you know that delta B1 plus delta B2 plus delta B3 plus delta B4 should be equal to 0, right? Because originally this support should be equal to 0, the diffractions. And in the same way, delta C1 plus delta C2 plus delta C3 plus delta C4 should be equal to 0. And then delta D1 have the same approach. Well, actually, from here, you can see that you need to solve for 3 equations for 3 unknowns. So if you have very high degree of indeterminacy, then there will be a very large matrix to be solved, okay? And then it will becomes quite complicated when the degree of indeterminacy is high. So here we introduce you another method which called the displacement method instead of force method. On the left-hand side, you can see that we will choose one of the redundant support reactions, and then we will take it away. Say, for example, we will take the YA away, and then we will find the diffractions, and then from the diffractions, we can find for these redundant support reaction YA. For the displacement method on the right-hand side, you can see that actually the diffraction at A, YA, is actually equal to 0. And theta A actually is an unknown here, while the diffraction at the B also equals to 0, and then theta B also equal to 0. And then for the displacement method, actually we will from the unknown support, unknown rotation, and then to find out the support reactions. So for here, actually, for the displacement method, we will try to find the unknown from the rotation or from the deflections. So we call that as displacement method. So before we introduce you the way how to calculate, so first of all, we would like to let you know what is NOx. Well, if you have a member here, say for example, you have a beam, NOx actually means the specified point at the ends of the member. So for here, we have 2 NOx, okay? Or actually, if I have a support in between, I'll call this at 1 NOx, and then this one at another NOx, okay? And here maybe it's another NOx, okay? So for this NOx, actually, it will have some displacement or it will have some rotations. And for this displacement, we call that as degree of freedom. Say, for example, for this NOx, actually, I have a support here. One is pin support, one is the roller support, and then you will have rotation. So here I will have rotation A, here I will have rotation B. So for this one, I call that this one have 2 NOx, and then here have 2 degree of freedom. Because I will have 2 kinds of displacement. Okay. But I will give you more example, and then you will know what I mean. For here, you can see that I have a NOC A here, and I have a NOC B here. Then actually, I apply some loading on the structures. Then NOC A will have the deflections equal to 0. Because here you can see that the deflection at A should be equal to 0 because I have a roller support here. But I can have a rotation at A. This one is not equal to 0. While the deflection at B again equal to 0, and then the rotation at B is also equal to 0. So for here, I have 2 NOCs, but just at the NOC A, I can have rotation. So for here, I call this one as 1 unknown degree of freedom only. That means I just can have 1 degree of freedom. Just the point A can have rotation. So for this system, I call that the degree of freedom is just equal to 1. Just 1 NOC, and then with 1 rotation only, okay? And then for here, you can see that for these structures, if I add the load here, then actually at the point A, that means NOC A, then I can have rotation at A, but no deflection. And at B, actually, I can also have rotation, but no deflection. In the NOC C, I have both deflection and then I have rotation. So for this one, I call that has 4 degree of freedom, which is called theta A, theta B, theta C, and delta C, okay? Because at 3 NOCs, I can move in 4 different ways. Theta A, theta B, theta C, and then I have deflection as C. So I call that this one as 4 degree of freedom. Okay? They are actually theta A, theta B, theta C, and delta C, okay? And in the beam below here, you can see that I have 3 NOCs, A, B, and C. All of them can have rotation only, but they do not have any deflection, okay? So for this one, I call that they have 3 degree of freedom for this beam. It can only move in 3 ways. That means they can rotate at A, rotate at B, and rotate at C, okay? And then for this frame, you can see that both A and D actually cannot move and cannot rotate because they are fixed end support or fixed support. So for this one, the theta at A is equal to 0, and delta at A is also equal to 0. D as well, theta D is equal to 0, and then delta D is also equal to 0. When you apply the load, just the point B can rotate, and then the node C can rotate. So you have just degree of freedom, theta B and then the theta C, okay? And then if you apply the horizontal load, assume that this delta is equal to delta. So you have delta here as the first degree of freedom. And then at the B, you can rotate, so you have theta B. At C, you can also rotate. At D, actually, the diffraction is equal to 0. And just the rotation at D is not equal to 0. So for this frame, you have 4 degrees of freedom. Then right now, you know that actually for a beam or for structures, actually we have rotation and then we have deflections, okay? So in general, you can see that I have a beam here. I have 2 nodes here, as you can see. 1 node here, I can call it as A. And then I have a node here, I call it as a B. So in general, I can have the degree of freedom, theta A. That means I can have a rotation about A. And then at the node B, I can have a rotation about B. And then you can think that actually for the support, actually you can have deflection. So you have a delta here. So these are actually the degree of freedom, right? That means it can move. And actually the loading, W and P, it can also create some member ends moment to the structures. Right now, I want to write an equation. MAB and MBA, I call it the member ends moment. If I have a member here, then there must be moment at the ends, right? This is the member. Then I must have moment at the ends. For here, I call it as A. Here, I call it as a B. Then for here, I must have a member moment MAB. For here, I must have a moment MBA. Okay? That means at the ends of the member, I must have moment inside the member. Right now, I want to write down the relationship of MAB and MBA in terms of, this is function of theta A, theta B, delta, and W. I want to write an equation between the moment at the ends of the member with the theta A, theta B, the deflection of the structure, and then the loading within the beam. Okay, I want to write an equation. So I call that the slope deflection equation. Slope is actually theta, and then deflection is actually the delta. Also, there will be loading on the member. So I want to write down an equation between the member end moment and theta A, theta B, delta, and a W. You know what I mean? Okay, I will let you know soon. Right here, you can see that if I have a member at the end, I call that MAB. That actually will create a rotation, theta A. Then what is the relationship between MAB and theta A? What is the relationship between them? Can I write an equation just between MAB and theta A? Now, actually, I can use the so-called conjugate beam here. If I have a moment MAB here, then it will induce the same moment at the ends, actually, because of equilibrium. If I have MAB here, then I should have the same moment here to balance the moment, okay? MAB here and MAB here. And then for that, if I want to know what is the theta A, if you still remember, theta A for the conjugate beam, theta A is equivalent to the shear, the conjugate beam. Okay. So for the conjugate beam, it will be the M over EI, the loading. So this one actually will create the moment like this. And then the inside moment here will create the loading like this. But this is the derivation. You do not need to know about that, but I just show you why they have something like this. Then if you want to find the rotation at the A, actually you find the shear at A of the conjugate beam, then you can find the rotation at A. Okay? Conjugate beam. Do you still remember what is conjugate beam? If you want to find the rotation, you just need to find the shear. From the shear of the conjugate beam, actually it is equal to the rotation of the real beam. So here the loading actually is equal to M over EI, if you still remember. The W is equal to M over EI for conjugate beam. So if you have a moment like this, actually this is your loading. This something like this. This is the moment diagram. Then after showing, after using the so-called the conjugate beam, you can show that the MAB is equal to 4EI over L theta A. So this is the relationship between the member end's moment and the theta. So MAB is equal to 4EI over L theta A. Do you agree? And then by the same token, actually, we will set the so-called the theta A is equal to 0 here, and then the deflection also equal to 0. And then here, the deflection is equal to 0, while just theta B is not equal to 0. I want to see what is the relationship between MAB and the theta B. As I mentioned, I want to find out the relationship between the moment, theta A, theta B, delta, and the W. Okay? I want to develop an equation like this. So first of all, I will set theta B equal to 0, delta equal to 0, and then W equal to 0. First of all, I want to know what is the relationship between the moment and the theta A. Then I find that it is equal to MAB 4EI over L theta A. Okay, afterward, I have find the relationship between theta A already. Then the next one, I want to find what is the relationship between MAB and theta B. Then I will set this one equal to 0, this one equal to 0, this one is equal to 0. And then I will take a look what is the relationship between theta B and MAB. And then I found that actually MAB and the theta B have this relationship, which is 2EI over L times theta B. Okay. So you can see that I set theta A, delta A equal to 0. And then I set delta B is also equal to 0, while theta B is not equal to 0. Okay. So I find the relationship between MAB and then the theta B. For the next one, actually, I want to find what is the relationship between delta, that means the deflection, and the member end's moment. So right here, you can see that it is a fixed end on both sides. So theta A is equal to 0, delta B is equal to 0. Sorry, this one is A as well. So for here, theta B is equal to 0, and then delta B is equal to 0, right? Both are fixed end, but I just have a deflection. So I want to take a look, what is the relationship between member end's moment and the delta? Well, I said this one is equal to 0, this one is equal to 0, this one is equal to 0. Then I just have delta, right? So with delta, I want to find out what is the moment. So for here, actually, I will do that by putting the right-hand side equal to the delta. So you can see that if I put that equal to delta, again, I use the conjugate beam, I can say that the MAB is equal to negative 6EI over L squared times delta. But here is actually the proof by using the conjugate beam. But I don't require you to know the proof. You just need to know if I have a deflection like this. That means you turn in this way. The angle, if it is clockwise, then actually it will create a moment of negative 6EI over L squared delta. Okay. And then finally, I want to know if, because the MAB is here, and I want to find the relationship between theta A, theta B, delta, and then the loading in between, I will set all this equal to 0. And then, well, the W is not equal to 0. So you can see that both sides are fixed end. If I add the low W here, actually you will have the so-called fixed end moment on both sides. Okay. So I call it this is a fixed end moment on AB. While this here, I will have fixed end moment, BA. That means I will have fixed end moment on both sides. So I just have a table will be given to you. When you apply the single law here, then you will have a fixed end moment on the left-hand side and then on the right-hand side. If you have two law here, actually you have a fixed end moment here and then you have a fixed end moment here. Okay. So by combining all the things, then I will just have this equation. MAB is actually equal to 4EI over L theta A. We have calculated for that. MAB also equal to 2EI over L theta B. MAB also equal to negative 6 delta EI over L squared. And then MAB also equals to fixed end moment. You just add these four together. Because this is the relationship between moment and theta A. This is the relationship between moment and theta B. This is the relationship between moment and the delta. And this is the moment between the fixed end, the loading. Because this fixed end moment, actually you can see that it relates to the loads you apply. If you have a P here, then your moment here is equal to the PL over 8. It relates to the length and then to the load applied at the center. You know what I mean? So actually you can develop a so-called the slope diffraction equation. You can write down the member N's moment here. This is member N moment. In terms of theta A, theta B, diffraction, and then the loading. Okay. So this is the so-called the slope diffraction equation. And then actually you will assume that clockwise is positive. So if you have a member here, here I will always call this MAB. Here I will call that as MBA. And then for MAB, I can write down this equation. And then for MBA, I can write down for this equation. Now, don't worry, this one is relatively simple, actually. Now, you can see this equation seems very complicated. But when you try to use it, it is not that complicated. I will illustrate to you very soon. So in short, actually, I can write down my equation like this. The moment is equal to 2ek times 2 theta n theta f minus 3 phi plus FEM. And mean year size, because actually you have a beam here, A and a B. If you consider the moment in this side, MAB, then A is the near side, B is the far side. So in this case, A is the near side, B is the far side. So for here, I can put theta A plus theta B, and then this N is AB. While K is actually equals to I divided by L. So this equation is easy to memorize. 2EI over L, 2 theta A plus theta B minus 3 sine, and then plus FEM. This is the MAB. Phi actually means delta divided by L. That means if you have diffraction here, then it is delta, then this is delta, and then this is the length. The phi we call that as chord rotation. That means the whole member have diffraction. Then it will have the so-called the chord rotation here, while this delta is the diffraction of the member, L is the length of the member. Okay? If it has diffraction, like you have support settlement, then you will have the delta. If you don't have any support diffraction, then the phi, this phi, will be equal to 0. If no support rotation, support diffraction. So for each beam, actually, we can write down these so-called the slope diffraction equations. And then from these slope diffraction equations, we can find for the unknown member ends moment. And once you find the member ends moment, then actually you can use equilibrium to find the shear, and then you can find the so-called the shear force and the bending moment diagram. Okay, let's take a break of 5 minutes, okay? And then after coming back, we can have some illustration to you how to use this equation. I will use the equation here to show you how to find the member ends moment, okay? Just take a break of 5 minutes and then come back. Okay, for the beam like that, now we can actually cut the free body diagram. For the beam AB here, actually I can cut it. Actually, there's a moment MAB here. And then there's a moment MBA here. This is actually the member in the moment. I mean the moment in the member. Okay. That means I cut the free body diagram here, and then I cut a free body diagram here, and then you have actually the moment inside the member. Okay. And then I also cut the member here. I also cut the member here. And actually, I also have a moment in this member. I have a distributor load. And then again, I will have a member and moment here, MBC and MCB. Okay. So my member ends moment, actually, I can write down the equation. MAB here is equal to 2EI over L 2 theta A plus theta B, and then minus 3 phi, and plus fixed end moment, AB. Okay, this is my member end moment, or member moment. Right here, you can see that for this support, it is a fixed end support, right? So how about what is the theta A? It cannot have rotation, right? Because theta A is a fixed end support. So theta A is equal to 0 here. So for here, this equation here will be equal to 0. And then when I apply the load here, you will deform like that. So I will have a theta B here, and then I don't know the answer. So I will keep theta B here. And then for here, for all the support, actually there's no deflection at the support. So this one is actually equals to the deflection divided by the length. And this one is also equal to 0 because there's no support settlement. And then on this beam, actually there's no loading. You can see that there's no loading applied on the top. So this one will be equal, you will also be equal to 0. So for the first member end moment, I will have MAB equal to 2EI over L and times theta B. So this is my equation, okay? So for here, you can see that I can write down my first equation like that. Of course, my L is equal to 8 meters. Because for here it is equal to 8, so I will put L is equal to 8. So it will be equal to EI theta B divided by 4, okay? So this is my member end moment for the first member end moment, right? So I will get this one. Do you agree? Because theta A will be equal to 0, while I don't know theta B, and then support reaction, the support settlement is equal to 0. And then I have no loading applied on the top of the beam, so it is equal to 0. Okay? And then for MBA, is actually the moment right here. I can write down similar thing here. If B first, then B becomes the near side, so I will have 2 theta B. The far side is A, so plus theta A, and then minus 3 phi, and then plus FEM, fixed end moment, BA. Again, theta B is not equal to 0, because theta B can rotate, right? Well, theta A is a fixed end. So I will put this one is equal to 0, and then I have no support settlement, so this one is equal to 0. And then I have no loading on the top of the beam. So the fixed end moment is equal to 0. So I will have this one, 4EI over L, theta B. This is my second expression. And then 4, you can see that the length here is again equal to 8. So it becomes EI theta B divided by 2. So it is the thing here. Do you agree? Do you know what I mean? So you can write down the member moment with theta B, right? Once you find theta B, then you can find the moment. Do you agree? Okay, we can continue to write the equation. Of MBC here, again, you can see that there's theta B and then the theta C is equal to 0 because it is a fixed end moment. I mean, fixed end, right? So for here, I have a beam here, I have a distributed load here. Then this is my moment MBC. This is the moment MCB. Then I can have my equation MBC is equal to 2EI over L, 2 theta B plus theta C minus V phi plus FEM BC, okay? I know that theta B will rotate while C is equal to 0. So I put this one equal to 0. I have no support settlement, so it is equal to 0. But due to this loading, you can see that I have a triangular load here. Then I will have a fixed end moment due to this load, due to this triangular load. Okay, so what is the fixed end moment? From this table, I can see that if I have a triangular load here, then I will have the fixed end moment like this, right? Because I have loading in the beam, it will create on the both sides with a moment, right? Then I know that on the triangular side, actually it is equal to WL squared over 30. So on this side, actually, I know that I will have a WL squared over 30. Then I know that the length is equal to 6 meters, and the W also equal to 6. So actually, I will have a moment here is equal to negative 7.2. So I know that actually I will have a moment here which is equal to 7.2. You know what I mean? Because I have a load here, W is equal to 6 kN per meter. So this one is equal to 7.2. Because as I mentioned, clockwise will be positive in this method. And then this fixed end moment will be counterclockwise. So actually it is negative 7.2. You know what I mean? Because for the fixed end moment, if I have a load here, I have a triangular load here, I don't have rotation, theta is equal to 0, deflection also equal to 0, theta is equal to 0, and then deflection is equal to 0 on both sides, then actually due to this loading, there will be a moment created in your member. Because when you apply the load, you do not have any rotation, then automatically there will be a moment created, which is equal to WL squared divided by 30. You know what I mean? So as I have a triangular load here, and then the loading, the magnitude is equal to 6, and then the length is equal to 6 meters. So I will automatically create a moment as this end, which is equal to 7.2. While on the other side, I will have a moment here, which is equal to 10.8. This is due to the loading applied. So for here, I will have this, and then with negative 7.2. And then you know that the length is equal to 6 meters. So it will be equal to 2 EI over 3 theta B, and then minus 7.2, which is equal to MBC. So from here, you can see that it is 2 over 3 EI theta B minus 7.2. Do you know what I mean? And then finally, because you have an angle here for the MCB here, here is MCB, actually is equal to 2 EI over L. And then the near side is C, the far side is B, and then minus 3 phi, and plus fixed end moment, BC. Now the fixed end moment will be something like this. Because the fixed end moment on the right hand side is on a clockwise direction, so it is a positive answer. So for here, theta C is equal to 0. And this phi is also equal to 0. So you have 2 EI over 6 because the length is equal to 6 theta B and then plus 10.8. So it becomes EI theta B divided by 3 plus 10.8. So that's why you have this expression. Now, hopefully you know what I mean. You can see that actually we can write down the moment in terms of the rotation, theta B. So you can see that you have 4 unknowns. You have MAB equals to EI over 4 theta B. You have MBA equal to EI over 2 theta B. You have MBC, which is equal to 2 over 3 EI theta B minus 7.2. And then you have MCB EI theta B over 3 plus 10.8. So you can see that theta B is the only unknown. If you once you know theta B, then you can find all the member moment. Then how can you find the theta B? Now right here, you can see that you have the member end moment here, MAB, MBA, MBC, and MCB here. If you take a look to this location, then actually you have member MBC on this side, because on the right hand side, it is in the clockwise direction. So right here, you have counterclockwise direction. And from here, you have clockwise direction. So here you have counterclockwise direction. So you can see that MBA, that means this one, plus MBC, these two must be in equilibrium, right? So this one, when they add together, must be equal to 0. So MBA and MBC, you have already the expression. MBA is here, MBC is here. That means you are adding these two together, it is equal to 0. MBA plus MBC equal to 0, right? So you have this equation plus this equation equal to 0. Then from this one, you can find the values of theta B. So right here, you can find the values of theta B, which is equal to 6.17 over EI. Once you find theta B, you substitute back to the expression, then you can find all the member ends moment. Is it amazing? Without finding the support reactions, in the force method, you need to find the member. You need to assume the redundant support reaction. You take it away, and then you recalculate, and then you can find the redundant support reaction. And then right here, you can immediately relate the member end moment with the deflections theta here, and then the deflection. I mean the support deflection if there's support reaction, but there's no right here, just the support rotation. Okay. Then immediately you can find the member end moment. Okay. With the member end moment, actually you have this 1.54, you have this 3.09, you have this 3.09, and then have this 12.86. Then actually you can use equilibrium to find for the shear. You take moment here, and then you can find for the shear. You use vertical force equilibrium, then you can find for the shear on the both sides. Right? If you have these member end moment, then you take moment here, then you can find a shear here, and then you use vertical equilibrium, you can find a shear on the other side, right? So you can find for all the answer once you find the member end moment. You know what I mean? I will demonstrate another one for you. Now you can see that here actually again there's another beam. You have a fixed end at the A, you have a pin support at B, and then you have a roller support at C. So actually, if you cut a three-body diagram, you have a moment here, MAB, and then you have a moment here, MBA, and then here you have a moment MBC. Right here, actually, it is a roller, and they actually have no member moment. Okay. But in order to simplify your calculation, actually, when there is a roller support at the ends, we have actually another equation for you that you can use. Say for this case, you have a rotation here, and then you have another one here. Then say this is A, B, C. Then you have a member end moment here, MAB. Here you have a member end moment, MPA. Here you have a member end moment, BC. Then for MBC, you can actually use this expression, which is equal to 3 EI over L. And then you can use theta B minus phi here, plus FEM at B. You can use this equation. It is a faster one. Okay. You do not need to use the original one. The original one is something like this. This is the original one. Can you see the difference? Here you still have the theta C here, right? But if this is the end with a roller here, actually you can use this one instead of using this one. If there is a roller at the ends, then actually you can use the modified equation MBC. This one actually will be faster and easier to substitute. Because for here, why we have this expression, because we already find that the member end moment at the roller is equal to 0. So originally, if you want to prove, actually this is also simple. I can prove for you if you want. This is your member. Say for here, you have a roller. For here, actually, you have a moment M. Say for this MAB. This is actually MBA, right? MAB is actually equal to 2EI over L, 2 theta A plus theta B minus phi phi plus FEM, maybe, right? MBA is actually equal to 2EI over L, 2 theta B plus theta A minus phi phi plus fixed end moment, BA. However, you know that MBA and FEMBA must be equal to 0 because they are the free end, or not free end is the pin support, right? So this one will be equal to 0. This one will be equal to 0. Do you agree? So you will have 0 here, 2 theta B plus theta A minus phi phi. This equation will become this one. So actually we can eliminate the theta B. So the theta B we can write on this side. And then we can have half here, theta A minus phi phi. And then for this one, actually I can substitute to here. Then you can eliminate. It becomes phi EI over L theta A. And then here becomes phi phi EI over L and times FEM. So if you take the phi EI over LL, it becomes theta A minus phi and plus FEM. So this expression is actually have been proved for you, MAB here. So this is the proof. And then you can see that actually they are the same. For this expression, actually you can see that they are the same. While K is equal to I over L, theta n is the near side, so it is theta A minus phi plus FEMAB. That means it is actually the simplified expression for you. Then actually you can use this expression once you have the pin support at the ends. Then you can use this expression for your member end moment. Then actually you can use this expression to calculate for the example. So for here, we can again use the expression for MAB and then for MBA. While for the MBC, we can use VEI. For MAB and MBA, we can still use this 2EI over L, 2 theta A plus theta B minus phi phi, and then FEM for MAB and MBA. While for MBC, actually we can use VEI over L, and then theta B minus phi, and then plus FEM. We can use this expression for MBC because the far end of this member is equal to 0. I mean, it's a pin support. So for here, actually, for the fixed end moment, we know that for the beam AB, for the part AB, actually, we have a fixed end moment like this. And then for the fixed end moment, actually, it is equal to WL squared over 12. And then for here, for this beam, if it is having a fixed support on one side and then a roller on the other side, then actually the fixed end moment is equal to 3PL over 16. So if I have a case like this, I have a fixed end here, and then I have a beam support here. If I have a loading, which is equal to P, then I have a length L here. Then I know that I will have a moment equal to BPL divided by 12. Sorry, it's divided by 16. So that's why I actually have a fixed moment or fixed end moment equal to negative 22.5 kN. So I have a moment here, which is equal to negative 22.5. So again, I will use this expression for moment AB here, and then for moment BA here, and then for the moment BC here. So still 2EI over L, 2 theta n minus plus theta far n minus 3 phi, and then plus the fixed end moment. And you know that for the location A, actually it is a fixed support. So theta A is equal to 0. So right here, you can see that we put theta A is equal to 0. And theta B actually, for the point at the B, I mean the node B can rotate. So we keep theta B here. And there's no support settlement. So we put this one is equal to 0. And because of this distributed load, we have the fixed end moment equal to negative 120. So for the first moment, actually it is equal to 0.333 EI theta B minus 120, okay? And then for the moment MBA, actually again we have 2 EI over L. And then for here, theta B we don't know. So we will have 2 theta B. And then theta A we know that it is equal to 0. And there's no support settlement. And then on the right hand side, actually there will be a fixed end moment equal to 120. So the expression for MBA is equal to 0.667 EI theta B plus 120. And then for the member, I mean BC here, as I mentioned, you can use this special expression. 3 EI over L and then times theta n minus phi and then plus fixed end moment. For here, you can see that because we do not have support settlement, so this one is equal to 0. And then the fixed end moment we just calculate it is equal to negative 22.5. So we have an expression 1.5 EI theta B minus 22.5. And then for this one, actually, we can have a support, I mean, for the equilibrium, it's actually MBC plus MBA is equal to 0. Now you just take a look to the joint here, always take a look to a joint here. And then the moment MBC plus the moment MBA, I mean, MBC plus the moment MBA should be equal to 0. Because at this joint, actually you will have a moment like this, which is MBA. And then you should have a moment like this. This is the moment MBC. And MBA plus MBC must be equal to 0. Okay, because of the equilibrium of the joint. So this MBA plus MBC must be equal to 0. Okay, this joint. MBA plus MBC must be equal to 0. So you just use this expression, MBA plus MBC, this 2 is equal to 0. Then you can find the values of theta B, right? Once you find the values of theta B, you can substitute it back to your equation. Then you can find MAB, MBA, and MBC. Now I need to remind you for here, negative means clockwise. Sorry, negative means anti-clockwise. And then positive means clockwise. Negative means anti-clockwise. If I write down my equation, MAB is here, that means MAB is counterclockwise, MAB, which is equal to negative 135. And the MBA, it is positive, means that it is clockwise. And the MBC is negative, means that it is counterclockwise. Okay? So for this one, actually, you can see that it will have something like this. This one is counterclockwise, so it is negative. This one, 90, it is clockwise. This one, it is anti-clockwise. If you use this method, it will always assume that clockwise is positive. Okay? So you define the direction first. But when you draw the shear force and the bending moment diagram, still, if it bends downward, it is negative. it bends upward, then actually it is positive. Do you know what I mean? The clockwise and counterclockwise, just for you to write down the direction of the moment first. But to define whether it is positive or negative moment, it still use our conventional way to define, okay? Finally, for this one, I want to give you an example with support settlement. So you can see that for here, I have the first beam here, AB, and there's another one is BC, and another section is CD. You can see that. And then for this one, you can see that actually there will be a support settlement at location C. And it will create a downward settlement at the location C. So for here, you can see that there is a chord rotation. This is due to delta divided by L. So the delta is 30 mm. So it is 30 mm divided by 6,000, because this is meter, okay? So this is the chord rotation. Now, remember, when the chord rotation is clockwise, then it is positive. Okay? So you can see that originally it is horizontal. It moved to this one, so it rotates in a clockwise direction. Now for the other side, originally it is horizontal. It becomes something like that. That means it rotates in a counterclockwise direction. So this one is a negative value. So if the support settlement will make it go down, say for example, original here, it rotates to here. That means it will defect like that. Originally it is flat, then it is clockwise. However, for this side, actually, originally it is here. So if you think that actually it is originally horizontal, then that means it rotates in a counterclockwise direction. Then for this one, it is negative. This one is positive. Okay, you need to know how to define positive and which one is negative. Okay. Then again, you can write down your slope deflection equation for the section A, B, B, C, and for the CD. So for here, you can see that you can write down MAB, MBA, MBC, MCB, MCD, and MDC. Because for this one, you have 6 member ends moment. Okay, and then you can write down one by one. But for here, you can see that both theta A and theta D are at the fixed support. So theta A and the theta D is equal to 0. While theta B and theta C actually can rotate. So you should not set it to be 0. So you can see that this is E, and then this is I. This is E, and then this is I. And then for theta A, actually it is equal to 0 because it is a fixed support. Theta B is not. And then theta B delta at the location B, there is no support settlement, so it is still equal to 0. And then at here, there's actually a fixed end moment, which is equal to 86.4. So you have negative 68.4 here. So that's why you have the expression MAB equal to 3333.3 theta B minus 86.4. And then for MBA, you have also this EI here. And then you know that theta A is equal to 0. Then there's no support settlement at A and then at B. And then you know that because of the loading, there will be fixed end moment, which is equal to 86.4. And then for BC, actually, there's no loading. so the fixed end moment is equal to 0. And then you know that both theta B and then the theta C is not equal to 0. So we will keep theta B and theta C here. So you can see that for the expression of MBC, there's theta B and there's theta C. And MCB, again, you have this EI, and then you have this theta C and then this theta B. 0.005 is actually the chord rotation, because actually you know that at the C, actually you will have deflection. It will deflect like that because it will go down for 30 mm. So this one is actually 30 divided by 6,000. So this one is 0.005. And the MCB actually also rotate the same, so actually it is still 0.005. And then for the span CD, actually it will rotate again, so you will have 0.00667. Why the value is different? Actually, because again, this one it will deflect for 30 mm, while the length of the member is 4.5 meters, so it is 4,500. So you will find that the value is equal to 0.00667. And then you will have the expression like that. And then you can see that you have two unknowns, theta C and theta B. So you need to find the values of theta B and theta C. Then you can find all the member ends moment. So for here, you have two supports. So you have MBA plus MBC is equal to 0. And then you have MCB plus MCD is equal to 0. Okay. That means you have two equations and then you have two unknowns. And then once you solve theta B and theta C, you can substitute them back into these 6 equations. And then you can find for all member ends moment. So this is the member ends moment. And then once you find the member ends moment, you can find the remaining shear. And then you can plot the bending moment and then the shear force diagram. Okay. Okay, now actually it can also be applied to the frame structures. And then I will leave it for the next lecture. Okay. Okay, so I will stop the recording first. 首先講一講先，測驗嘅 arrangement 咧，由於12號sorry 原身就話12號嘅，但係因為都有同學有時間撞咗，咁所以咧我哋會再褪一個禮拜，我哋會去褪到去19號嘅，係啊，褪多個禮拜，所以褪到去19號嘅星期六朝頭早，唔係星期六嘅夜晚 ，OK， 19號啊，19號嘅夜晚。咁會係喺7點至9點 ，OK？ 11月19號，因為有同學12號唔得閒 ，OK？ 咁同學 reserve 個時間啦。咁19號，我哋會翻嚟學校1011，即係上面嘅電腦室嗰度考 ，OK？ 考到第5課嘅啫，考到第5課 ，OK？ 咁距離而家咧仲有都差唔多2個禮拜時間啦。咁你哋可以自己溫下書啦。咁咧就下個禮拜3咧就唔好意思，日頭嘅同學咧，因為我嗰日晏晝咧我有啲事咧，我上唔到堂，即係下個禮拜3咧就要上唔到啦。咁一樣咧，下個禮拜3上唔到都係呢個時間同各位上返 ，OK？ 所以下個禮拜4同樣時間喺呢度上，下個禮拜3嗰堂咧。因為我有個會要開，咁我就join 唔到個堂，咁就禮拜4同一時間，你哋上返啦，好嘛 咁就我都會 send 翻嗰個MS Team 俾你哋，我會擺上 Moodle，咁你哋就照 join 翻入嚟啦，好唔好啊？唔好意思。OK， 咁或者我今日就講到呢度啦。各位同學有冇問題？係。
我想問 lab 咧係咪12號開始啊
？lab 係12號。
5號嗰個留咯嗬。
5號嗰個唔需要啦，因為有同學5號唔得閒。
收到，唔該。
係啦，咁所以12號咧，你哋翻嚟上 lab 就得啦。而家講緊 part time 嘅同學 ，full time 嘅同學咧，lab 已經上晒㗎啦。係 part time 嘅同學12號翻嚟10點鐘啊。OK。
哦，即係跟翻 timetable 嗰個時間，但係淨係上1日12號。
係啦，就唔使上2日啦，上1日得啦。
好，
因為呢個禮拜6有同學唔得閒，咁就直情上下個禮拜就得啦。
咁下個禮拜個12號個 lab 係上幾耐時間會要長？
大約3個鐘內就上晒㗎啦。
OK。
3個鐘之內，咁你1點前應該走得啦。你10點翻嚟，1點前應該做完啦。
我見嗰度有3個 experiment 嘅 slide 全部 lab 都做到。
係啊，個3個 experiment 都要做啦。咁你哋咧要自己分組，大約5至6個同學一組啦。咁你哋將你哋個 group 嘅組員嘅名咧 send 翻俾我 ，OK？ 咁我就會 post 翻出嚟嘅，因為第時大家做 lab report 都要分組噶嘛。咁如果你話我都分唔到喎，咁你可以嗰日咧翻嚟做 lab 嘅時候咧分埋都得。咁分到就俾我啦，分唔到就嗰日做 lab 嘅時候就先分都得，好嘛 ？OK， 嗱講多次 ，lab 就12號，即係下個禮拜6；測驗就再下一個禮拜6，即係19號。OK， 測嘅範圍去到conjugate beam 嗰課，應該係講緊第5課啦，我冇記錯嘅話啊。
阿 Sir， 我想問下咧，個 room 101011咧係 DI 個學員嗰度嗰個10樓啊。
係啊，上邊電腦房10樓。
好，唔該。
Okay。好，咁你做完第一份功課啦，咁我跟手就會擺第2份上去㗎啦。咁所以咧就你第1份交完咧，我第2份差唔多我都會放上去㗎啦，好嘛 ？OK。咁冇問題，我哋今日到呢度啦。OK，唔該晒。